In this video, we're going to look at a new method of proof called proof by induction. So we're going to go through the entire process that one would usually go through by a proof by induction. We're going to look at how to find the answer to a problem without necessarily solving the problem. We're going to apply recursive reasoning to the problem to try to solve it, and then we're going to use that recursive reasoning to develop proof by induction. Alright, so here's the problem that we're going to be working on. Imagine that we draw a dot on a plane, and by a plane I mean an infinite flat surface. You can imagine a huge flat table, and you sort of draw a dot on that table. So we're then going to draw lines on the table so that they all go through that dot, that same dot that doesn't move at all. And the question is, if we draw n different lines, how many regions do the lines split the plane into? And let's see what we mean by looking at a couple of examples. Well, here's what happens when we have one line and then you see that little dot in the middle. And then what happens is you have a region on the left and a region on the right. One line splits the plane into two different regions. Now, if we had two different lines, again, both lines go through that same dot. You can see that those lines split the plane into four different regions. And if you have three different lines going through the same dot, you can see that splits the plane into six different regions. And by now you probably see the pattern that however many lines you have twice as many regions. In other words, if there are n lines, then there are 2n regions. Now it does seem obvious that this pattern will continue, but just knowing the answer and being supremely confident that that answer is correct does not count as a proof. So we're going to have to find a way to prove it. And the way we're going to do it is through something called recursive reasoning. So recursive reasoning happens when you have infinitely many things that you have to do in principle, but you want to be able to give instructions in a finite way. So you have infinitely many cases to prove. In this case, you have a different kind of almost a different theorem to prove for each natural number, the natural number representing the number of lines. So what we're going to do is we're going to figure out the first case by ourselves, which actually we already did, so we don't have to worry about that. Then for the other cases, we're going to use the case that you just did to help you find the formula for the next case. So in other words, if we know what's going on with one line, we use what we know about one line to help us figure out two lines. Then once we figure out how many regions for two lines, we're going to use that to help us find out how many regions for three lines. After that, we're going to use the fact of what we know about three lines and figure out for four lines, etc. And then for the proof part, just to make sure the proof part works, we've got to prove that no matter where we are in the process, that we can always use the case that we just did to prove the formula correctly for the next case after that. Alright, so the first thing we're going to do is verify the first case. Suppose we have one line, and we already figured this one out. You have two regions, and 2 is equal to 2 times 1. One line, 2 times 1 regions, the formula works. So that gives us the n equals 1 case. Now, for the n equals 2 case, I'm going to ask myself, first of all, I'm not going to jump directly into going from n equals k lines to n equals k plus 1 lines. That is where we want to end up. We want to figure out what happens at every step in this process. Right now, I'm going to start small and just say what happens when I go from one line to two lines. So when I have one line, I have two regions. When I have two lines, I'm going to add another line. Now, I'm going to draw that line from one side of my original line to the other. And when I do that, if I'm going from left to right, part of that line has to be on the left side, no matter what angle it's coming in at. That is going to split region 1 into two other regions. And I've labeled those 1A and 1B. And if we continue that line, we can see that it's going to split region 2 into 2A, and two regions, which I call 2A and 2B. So that tells us we have two regions added when we added that extra line, and so we end up with 4 different regions altogether. And we get one region for each side of the point of intersection. One on the left side of the point of intersection, and one on the right side. Alright, so now we have 2 lines and 4 regions. Now what happens when we go from 2 lines to 3 lines? Well, we start with 2 lines. Now when we put in that third line, it's going to have to be a different line, but it's going to have to go through that common point of intersection. which means that it's going to have to be somewhere between those two lines that we have. So, something like this. It either has to go through region 1 or region 2 or region 3 or region 4. Has to go through one of those on one side of our point of intersection. And notice, just like before, it takes that region that used to be one region and splits it into two. And when we continue it on the other side, it takes that fourth region that used to be one region and splits that one into two as well. So and that gives us 6 regions altogether. What happened was 2 regions were added. Once again, one for each side of the point of intersection. One on the upper left side of the point of intersection, one on the lower right of the point of intersection. And so it looks like we have a pattern going on. So if we look at our most recent case, that's going to be n equals k lines, whatever k is, right? We're going to have k lines, and let's see what happens in terms of how many regions are added when we add that k plus 1th line. So how do we get from n equals k lines to n equals k plus 1 lines? Well, just like before, it's going to be a different line than any of the ones we have before. That means it's going to have to go between 2 of those lines, right? So the new line has to be between 2 existing lines. And for now, just for illustration, I'll show you between those 2 lines where the happy face is. None of this is going to be any different no matter which 2 lines that we take it between. And when we do that, that one region, again, just like before, gets split into 2 regions. And when we continue it on the other side of the point of intersection, that splits that region into 2 regions. So once again, a new region is added on both sides. We add 2 additional regions, and that means every time when we add a line, we add 2 regions to the total. Which means that if we know how many regions we have for k lines, we can figure out how many regions we have for k plus 1 lines simply by adding 2. So now what we're going to do is we're going to say, hey, let's look at the last case that we just did. And I'm not going to be, I want to be a little bit vague about what the last case was. It could be just n equals 1. It could be n equals 5 was the last case. Let's look at the last case where we got the formula that we think is true. We know it works for one line. We get 2 times 1. But who knows? What if for k lines we have 2 k regions? So what happens if the formula works at some point in our process? What happens when we add one more line to get k plus 1 lines? Well, what we want to show is that the formula still works. We still have twice as many regions as we have lines. So if we have k plus 1 lines, we would want 2 times k plus 1 regions. Well, we did prove that when we go from k lines to k plus 1 lines, we add 2 regions to our total. Well, back in the old days, we had 2 k regions for k lines. If we add 2 regions to get the k plus 1 lines, that gives us 2k plus 2 regions. And then we can factor out a 2 from that to get 2k plus 2 equals 2 times the quantity k plus 1, which is exactly what we wanted to prove. That's how many regions that we get for k plus 1 lines. So now we've proven 2 things, right? We've proven that when n is equal to 1, we have 2 times 1 regions. And we've proven that when we have, if we have 2k regions for n equals k, then we're going to have 2 times k plus 1 regions for n equals k plus 1. And it turns out these 2 facts are exactly what we need to prove the entire theorem, which is stated as follows. So if n is a natural number, we have, and if we have n distinct lines that all intersect at the same point, then they split the plane into 2 times n regions. And let me illustrate how the 2 facts that we proved in 1 and 2 at the top there give us exactly what we want for this theorem. So for instance, for n equals 1, well, we proved that one directly. So we just look at part 1. It says, yeah, for n equals 1, we have 2 times 1 regions. That's twice as many regions as lines. We're done. Now for n equals 2, that one, we know that for n equals 1, we have 2 times 1 regions. By part 2, it says if we have 2 times 1 regions and we add a line to get n equals 2, we're going to end up with 2 times 2 regions. So if you just plug in k equals 1 for part 2, it tells you exactly that. It tells you that if we have 2 regions, then we have 2 times 3 regions for n equals 3. Right? I'm sorry, 2 times 2 regions for n equals 2. Well, we do the same thing for n equals 3. We just proved that for n equals 2, we have 2 times 2 regions. And if we plug that back into part 2 up there, we know for n equals 3, we have 2 times, well, 1 more than 2 regions. So 2 times 3 regions. So again, we plug in k equals 2 there. It tells us that if we have 4 regions for n equals 2, then we have 2 times 3 regions for n equals 3. And we just keep on going. Now that we have a formula for n equals 3, we use part 2 to get us the formula for n equals 4. And we can keep on doing that for all values of n. So what that tells us is just by proving 1 and 2, two nice and finite results and theorems, facts, right? That proves the entire theorem. All right, so now what I want you to do is I want you to try out this process on the problem that I have outlined for you in Introduction to Induction, and that's on the PDF file included with this video.